So my name's Morton, and today I'm going to talk to you about Cassandra internals. Now, it's a pretty complicated code base, so we're not going to go into it in great depth, but what I am going to do is go through some of the more important classes and point to some of the places where things like exceptions and timeouts bubble out of the code and end up affecting you as a consumer of the Cassandra services. A little bit about myself before I start. I'm the co-founder and principal consultant at the last Pickle. We work with clients to deliver and improve Cassandra solutions. I'm a committer, DataStax MVP. I've been in the community for a long time, and we're based in New Zealand and Austin, Texas. So today we're going to talk about the architecture and then get in and actually look at the code. And architecture-wise, we can have a pretty simple diagram. There are some clients, they talk to APIs. APIs talk to some things we'll call cluster-aware software. That talks to some software that we can call cluster-unaware, which just takes things from memory and puts it on disk, takes things from disk and puts it in memory. When we put this together in a cluster, as you'd expect, the cluster-aware components start talking to each other, and the cluster-unaware components just keep doing their business. They don't have any concept of working with other nodes. We can put some better labels on this. This is, after all, a Dynamo-based system. So we can call our cluster-aware components the Dynamo layer, and we can call the cluster-unaware components the database layer. Cassandra is just a fast, log-structured database with a Dynamo layer on top that gives you results. So let's expand our agenda for today. We'll look at the code in the API, the code in the Dynamo layer, and finally the code in the database layer. I'm going to break the API layer up into a transport and a services component. At the transport level, we have Thrift. It's been around for a long time. We have a couple of implementations of the Thrift server. They're custom implementations, and the reason is that we do some cleanup when the clients disconnect, so we have to be able to have custom code there. If you do nothing, your call first enters into the custom T thread pool server. This guy has a thread pool in it. Each thread processes one client connection for the life of that connection, so it can take quite a few threads. The other server implementation that we have is the custom THS-HA server. You select this when you set the RPC server type to be HS-HA, uses a thread pool, but this time threads process one request response from a client and then move on to process one from another client. So it can use less threads if you've got a lot of clients in place. Now, we've also got native binary transport, and we've heard a bit about that today. And luckily it's in the code base, so we can have a bit of a deeper look at it. It used to be beta in 1.2, globally, generally available now. It uses Netty internally, and you can only use it with CQL3. And the equivalent of the T-server implementation here is the transport.server class. In these slides where you see OAC, I'm talking about org Apache Cassandra, so I'm pointing to a Java package, transport.server. When we start the server, we create an execution handler because we've got a thread pool here as well. And this thread pool works the same way as the HS-HA server. A thread processes one read request from a client and then goes on to process another one. To do that, it uses NIO for socket selection, and it sets up a thing in Netty called the server pipeline. This is a series of stages that your request goes through as it comes into the server and leaves. So there's frame encoding and decoding, frame compression and decompression, message encoding and decoding, up to a stage called the dispatcher, where we actually do something with your request. In the native binary, that dispatcher is in message.dispatcher, and it has this really nice, simple little function. It gets called with a message, we get your connection state, and we validate if we expect to get this message for this connection state. So if we're already authenticated, we don't expect to get an authentication message. Assuming we get past that, we then execute the request. That gives us a response to send back later on. Before we do that, though, we grab that connection state one more time and check to see if we should apply a state transition. So we've now moved into an authenticated state, for example. And then once we're done, We call channel write and we send the response back to the client. The messages that are involved in that native binary protocol are defined in a human readable protocol spec. It sits in the source tree. You can go and have a look and get a feel for everything that happens in there. That's the transport layer. On top of that, you've just logically got the service layer sitting. Now, JMX is a great feature of Cassandra and Java, and I encourage you to go and learn everything you can about how it works in Cassandra. If you want to find out, go and look at the interfaces. So the JMX management beans all implement interfaces. All those interfaces end with mbean. You can search for them in the code and find them. And they all have pretty good documentation on them to explain the functions and the properties that they have. And they're implemented in a way that makes a lot of sense. There's a storage proxy mbean. It's implemented by the storage proxy class and exposed as org Apache Cassandra storage proxy. So pretty easy to track down. Thrift works for us both at a transport and a service layer, double duty there. And its implementation starts in OAC Thrift Cassandra server. And this guy implements the entire Thrift interface. So it does what you would expect. It has access control. It has input validation. It maps to and from Thrift types into the native Cassandra types, as we don't use Thrift internally. And that interface, the Thrift interface, is defined in an interface definition language file. Sits in the code tree. It's not a human readable document. But if you go and have a look, you'll get a good feel for every function that's available on Thrift. So one of the more common functions that you're going to call is getSlice. We call this guy when we want to get a range of columns or some named columns from one particular row. This code example, Cassandra server.getSlice, is from 1.2 and beyond. So we set up request tracing. Might be active on this request. We get the client state. We have state in native binary and Thrift. And we use that to do some access control and see if you can read from this column family. And this is a pretty common function, reading stuff, so we've got to jump through a few abstractions here before we actually get to do the read. So if we drill down, we go to multi-get-slice internal, and this is where we get your Thrift request and we validate it. So did you ask us for minus 10 rows, something like that? And we create some objects that we're going to see a bit of called read commands. We pass those on to another function, and here we start to see the API and the Dynamo layer touching each other. This function takes read commands, an internal object, that does something with them and returns Thrift objects, the external API object that represents the results. To get that result, we make our last call in the API layer to read column family. This guy takes in a list of read commands and hands them to the storage proxy object, and we're done. This is where your API call ends, and we move into the Dynamo layer where we start to become cluster aware. Before we drill into that though, let's go back up and look at how CQL3 does it. The equivalent of the Cassandra server is called the query processor. Processes all the CQL3 statements, so it does exactly what you'd expect, has access control and input validation. It's used by both native binary and the Thrift interface. And instead of returning Thrift objects, it returns response messages from the transport package. So when this is used from CQL3, there's a little bit of packing that has to go on to transform it into something thrifty. The CQL3 language is defined in an ANTler grammar. Again, not human readable, but if you go and have a look, you can get a feel for all the keywords and the tokens and things like that are in there. Now in the grammar, there's a lot of statements. Those statements are processed in a two-phase approach. First, the ANTler compiler creates objects that we call parse statement, and this really just represents what you sent to the server. Tracks bound terms, and it has a prepared statement on it that is generally kind of complicated because it has to understand what it is you've asked the server and turn that into an object that we can execute later on. The thing we're going to execute is called the CQL statement. It's got access control and input validation on it, and if you look at the execute call, you can get a fair idea for how this is used. consistency level, passed in, variables, passed in, some other state, passed in. This is a reusable object that we can get some value out of. Again, the equivalent of get slice is probably the select, the most complicated thing in the CQL language. Its parse statement is implemented with an internal raw statement class. The prepare then creates our select statement. The select statement in the execute creates read commands. These are the same types that we saw on the thrift side of things. And it hands those read commands to the storage proxy, and that's the same storage proxy that we saw on the read side of things, on the thrift side of things, sorry. So your request by default using thrift comes into the custom T-thread pool server. If you're using native binary, it's going to come into the query processor, into the message dispatcher, sorry. Then it's going to come down to the query processor if you're in CQL3, or to the Cassandra server if you're on thrift. Either way, a read command was going to be created on the read path, and we're going to hand the read command down to the storage proxy. And now we're off and running, and we've got to worry about how many nodes are up and things like that. These are the packages that I think are in the Dynamo layer. We're not going to talk about the ones that are crossed out just for lack of time. So DHT is a distributed hash tree. It's where your tokens and partitioners are. GMS is where the gossip service is. Locator is where the strategy and the snitch live. And streaming's the last one there? Yeah, streaming is where we do anti-entropy. Where we stream data for anti-entropy. So back up into the service package, the storage proxy that we used before, this guy's the workhorse of everything that happens at the cluster. All the reads and writes go through this. So imagine what it does, and you'll probably be right. It's going to pick the endpoints. It's going to make sure that the consistency level is there. It's going to send messages to stages. We're going to learn about stages shortly. And then wait in a very efficient way for those messages to come back. Deal with our eventual consistency world, so storing hints and things like that. And then return the result back to the API. There's another important class in this package called the storage service. And this guy's a wrapper for a lot of other functionality that might be implemented elsewhere. It takes care of all of our ring operations, mapping to and from nodes and token, starting and stopping thrift and native binary and things like that. So if we're doing a read, storage proxy is going to use the storage service. It's going to find a bunch of nodes to send the read to. And when it gets the results, it's going to have to work out, do they match? If they don't match, how do they not match, and how do we deal with it? And that's handled by objects that implement the iResponse resolver interface. Pretty simple interface, only got two functions on it. We call pre-process when we've got a message delivered. So we've got a response from another node, we're going to call pre-process, hand it over. Once enough messages have been delivered, we call resolve. And the implementation of resolve is different depending on the type of response resolver that we're using. The row digest resolver is used the first time we do the read, and we ask one node to return the data and the other nodes to return the digest. This resolver makes its own digest of the data that it got back and compares those to the other digests. If they don't match, it's going to throw a digest mismatch exception to say data's out of sync. If they do match, it's just going to return the data, and we can get on with things. And when they don't match and we get a digest mismatch exception, we run the read a second time. And this time we ask all the nodes involved to return their data. And we use the row data resolver. And this guy uses the timestamps and works out the correct result that we're going to send back to the client. It works out the delta between that correct result and all the nodes that participated in the read, and sends mutations to those nodes so they update themselves. Doesn't wait around for a response, and then returns from the resolve function and gives us the data that we're going to send back to the API. And lastly, the range slice response resolver is used if you're doing a get range call, because it's got to deal with the extra complication of nodes returning multiple rows, different numbers of rows. That's great, we have those on the read path. The write path, the response is just, I did it or I didn't do it, so we don't need that. What we do have on both is the idea of an endpoint, or a handler or a callback. This is something that implements iasync callback. And this is just a place for the messaging services that we're going to look at to deliver a message that's come from another node. So it comes into the response function. And we've got a great implementation of that in the read callback class. In the get function, we come in and we wait on this condition to be set. So we've got the thread coming in on the get call. We're waiting for the condition. The condition is set once we've got enough calls to response over here. And what we're waiting for is the number of nodes that you specified in the consistency level and that the data response was handed over. If it's not set in the timeout, and that timeout is the RPC timeout, so by default 10 seconds, we fail through, and now in the new stuff that's coming on with the rapid read response, whatever it was called, this is going to change a little. If it's not set, we fail through and we throw a read timeout exception. And that results in a timeout exception coming back to your client. So when you get it timed out, it comes out of this function. Hopefully it is set, and then we call resolve on the resolver. We get our result, or we get another exception. This comes together in a function called fetch rows on the storage proxy. We hand in a list of read commands, and we iterate through them. For each read command, we get a list of the live sorted endpoints. Sorted means that the ones that are closest according to rack and data center awareness are at the start, and they're the ones that we're going to ask to get the data back. For each read command, we create a row digest resolver, because this is the first time we've done this read. We use that to construct a read callback. And then from our read command and our read, we use our read command to generate messages, and we use that and the read callback and the messaging service to send those messages to stages on the local and the remote node. And the stages are the things you see in node tool TP stats. So read stage and mutation stage. Once we've done that for all the read commands that were passed in, so we're going to read 3 rows, we go through this 3 times, then we loop and we go to all of the read commands, the read callbacks that we created, and we call get. Now remember, get can be a blocking call. If we haven't got enough responses back, we're going to block. Hopefully we don't block for too long. So we call get, hopefully it doesn't block, but it could throw some exceptions. So if we get a row digest exception here, we remember that, and later on in this function, we run the read the second time using the row data resolver. If we get a read timeout exception here, then we throw it so that it gets back to the API layer and it can deal with it. Hopefully none of these things happen, and resolve just returns the data that we're going to give back to the client. And we group all those together, return them back from the function. So this messaging service that I was talking about lives in the net package. The net package has a transport and a protocol for all of our internode communications. We're just going to look at the protocol. It's a verb-based thing. There's requests and response messages that get sent between the nodes, just the sort of thing you'd expect. There's a mutation verb, and that's what we use when we want to do a read. There's a read verb. When the response is the request response verb. If we're doing node to repair, there's tree request and tree response and so forth. Now the message service has no idea what to do with these things. It's completely dumb. All it knows to do is deliver verbs to something that implements iVerb handler. So there's a map of verbs to the verb handler. And the verb handler interface is very simple, just says do verb. So now the messaging service is completely dumb. All it knows is that I've got the mutation verb and I can get to a verb handler to run it. So we've got an object, but we also need a thread to run on. So we have a map of message verbs to stages. Stages are just thread pools. They're the stages in our staged event-driven architecture. They're the things that you see when you do node tool TP stats, and you see read, mutation stage, blah, blah, blah. They're just thread pools. So now we can bring this together in the message service receive function. We've got a verb, we've got an object that can process that verb, and we know the thread pool that we want to run that on. So when this guy's called, we've got our message. We wrap that up in a message delivery task. This is just a runnable that we can put into the thread pool later on. We use the message type, the verb, to get a stage to run it on. And then we just drop our message delivery task into that stage and say execute. And this function is getting called on a thread that is just processing incoming messages on the socket from one remote node. So it does this and then goes about its business and goes and tries to get some more data off the socket. So we've got this thing that comes in, we very quickly take it and deliver it into a thread pool to get run somewhere else. Later on, hopefully not too later, the message delivery task gets executed. It looks at the time that it was created and the current time. Remember, it was sitting in a queue waiting for a thread. And if that time is longer than the RPC timeout, same RPC timeout we were talking about in the read command, in the read callback, if it's longer than that, and this is the type of message we can drop, reads and writes, then we drop it. We don't do anything. When you see a dropped message in the logs or in no-tool-TP stats, it happens in this call here. So we know that no one else is waiting for this. We saw before in the read command, in the read callback, that once RPC timeout has expired, we stop waiting. So this is load shedding. No one's waiting, don't waste your time doing the work. Again, hopefully that's not the case. And we call message service get verb handler. It gives us the object, our verb handler, and we say do verb, and we've delivered it. So we've taken your read command from the fetch rows function in the storage proxy. We've serialized it into a message. The message service has sent that. Come over here, we've gone through the verb handler, and now we're running on the correct thread on a remote machine. That's the Dynamo layer. This is a bit more complicated than that, but that's about all we need for now. Storage proxy and the storage service work together to know, the storage proxy uses the storage service to know which nodes to go to. The storage proxy uses the messaging service to send messages to remote nodes. If it's local, there's a little bit of an optimization in there. Those messages get delivered into verb handlers, and those verb handlers are running on the correct thread pool. The database is just a database. There's nothing scary about it. The packages we're not going to look at today, OAC cache, that's where the key cache and the row cache live. OAC IO is where the SS table reader and writer live, and the tracing package is where the tracing stuff lives. The concurrent package is pretty small. The main thing that's in here is the stage manager. So all this does is create some thread pool executors based on configuration. So at startup, it looks at your YAML file, gets the number of concurrent writes and concurrent reads, size of the number of flush writers and things like that, and builds a bunch of thread pools. And then it has a nice little function for us to just get the thread pool that we want to use. As I said before, the stages are just the things you see in no-tool-TP stats. And that's about it for that package. Now on to the database. It's handily in a little package called database. The thing that you think of as your key space is implemented in a class called table. That can be a little bit confusing when you start looking at the code, but that's where it is. We have one of these in memory for each key space that you've got running, and we just grab that guy with a static function called open all the time. And if we want to do something with your column family / table, we have to get a thing called a column family store. So your column family is implemented in a class called column family store. Same for your table in CQL3 is implemented in the column family store. The table in the code is the key space. If we're going to do a read or a write, we come in at the top level here. We go to the table and we say get row to do a read or apply to do a write. So our column family store, this guy is the implementation of the column family. To make it extra confusing, if we're going to do a read, we call get column family. In Cassandra, in the code base, a column family is just an ordered collection of columns. It could be a fragment of a row that's come in on a write. It could be a fragment of a row that's come back from a read. It could be what we're materializing when we're running through compaction. It's just some columns. It doesn't even have a row associated with it, just some columns. So every time you see column family in the code base, you're like, just some columns. Get column families where we call to do our read, but most of the action kind of takes place in get top level columns. That's where you can see the effect of caches and things like that. When we're going to do a write, we call apply. Signature on this has expanded a bit. It includes a secondary index manager as well. Decorated key here on the apply function. That's a key that is both the key that you've given us and the token that we've generated from the partitioner together. The idea of a column family pre-version 2 was encapsulated in an interface called iColumnContainer. Had a bunch of add and remove functions, the sort of things you'd expect to see, and had two implementations, one for a normal column family and one for a super column, because in the code back then, a super column just looked like a column family for a lot of the time, which is why all the developers hated super columns, because there was lots of exceptions in there. In 2.0, they're gone, because super columns are implemented as composite types, and so we don't have so many exceptions in the code. But finally, the idea of here are some columns in a list, in a collection, is abstracted down to I-sorted columns. A bunch of add and remove functions on it. And we've got a few implementations. The array-backed sorted columns is a fast thread unsafe structure. It's used on the read path only. That's where we know that there's only going to be one thread accessing it. The atomic sorted columns is used by the mem table. This is the one that gives us our row level isolation. So if we're going to update 50 columns, readers will only see 0 or 50 of those columns. To do that, it uses a data structure called snap tree, and it makes some 0 copy clones, updates thing, and does compare and set to push it back. And lastly, the tree map back sorted columns is used in a lot of other places, and it's a thread safe structure. Finally, something in the code that has the same name as we talk about in the mem table. If we're going to do a write, we call put. Here's our decorated key again, our column family, secondary index updater. If you want to find out how this stuff gets onto disk, have a look at flush and signal. You'll see then how we call all the SS table writers, and your stuff ends up on disk. And now here's our read commands that we saw all the way back at the API layer. Get row, we call it, we pass in the table, just our key space. And this is how we're going to start our read. There's a slice by names read command. In Cassandra, there's really only two things we read, well, three, kind of. There's two ways we read mostly. Slice by names means you said select foo bar baz, and we're just going to get particular named columns. Slice from read command means you said get me the first 10 columns, or something like that. There's some additional classes now in here for 2.0 because you've also got paging support in there. And the read commands use some things called the disk atom filters. And from this point on, it's just iterators all the way down. We can get a bunch of iterators for the mem tables. And we always say the column family only has one mem table at a time. In reality, there's only one that we write to, but there can be others that are sitting in the flush queue waiting to get written out. There can be others that are actually getting written out. We're still going to get those and read from them. And we also want to get the iterators over the SS tables, all the ones that your row is on. We've got a couple of implementations. They do as you'd expect. Names query filter is used when we're getting just columns by name. Slice when we're getting a slice of columns. The identity query filter is used when we want to read all the columns from the row. So let's put this together in hopefully something that's kind of digestible and hopefully something that makes you think there's just three things going on here. There's the API, there's the bit that knows about nodes, and then there's the bit that knows how to get stuff on and off disk. That's the biggest takeaway from today. It's just that simple. Inside it's a little complicated, but like that. So your request comes in, custom T-thread pool server, or the message dispatcher, and then down to the query processor, or down to the Cassandra server and onto the query processor. Either way, we create read commands, hand the read commands down to the storage proxy. Storage proxy uses the storage service to work out what nodes we should go to. It constructs a response resolver, uses that to construct a read callback, generates messages from our read command and uses those with the read callback to make calls to the message service. Message service delivers those messages onto the local and remote nodes. They are passed into verb handlers that are running on the appropriate thread pool. If we're doing a read, the verb handler goes through the read commands, table, column family store, iDisk atom filter, and a big mess of iterators down there. It winds back up, and our verb handler can't return the value because it's getting invoked on the read thread. It's miles away from the storage proxy. So it sends a message, sends a request response message back to the source node. So the messaging service receives the request response message, delivers that into the async callback, which hands it to the response resolver. Once it's got enough responses, it sets the condition. When the storage proxy has called get on that read callback, the condition is now set. We come through that condition. We get the result by calling resolver.resolve that we want to hand back to the client. We return back from storage proxy fetch rows, and now we're going to send the results back to your client. And that's all I have today. Any questions? Yeah, in the front.
So does the coordinator node get involved in creating the read commands?
Yeah, that's all happening on the coordinator. So the node that gets called on the API is your coordinator.
Okay, so what does it pass across to the data nodes or replicas? Does it just pass on the thrift?
Yeah, so we don't use thrift internally.
Right.
Yeah, so the thing that it passes is the read command gets serialized into a message, and those bytes just gets passed along. Question at the back?
On the security side, how is SQL injection prevented?
How is SQL injection prevented?
You compare it directly with SQL injection that you can get away with.
Use prepared statements, and I don't know all the parsing that SQL does.
Doesn't work with SQL, so it's only one query and there's no injection possibility.
Okay. Any other questions? Another one at the back?
In a couple slides back, you talked that the array-back sorted columns is unsafe, thread unsafe, because it's only one thread at a time. Why is that?
There was a big improvement in read performance in about version 1 or 1.1, and it was because that was added in for the most part. On the read path, we're reading stuff out of the iterators and getting the results together. So we're reading from all your SS tables, merging those results together into something that we're going to hand back. That array back sorted columns runs faster. It's only one thread, doesn't have to go through all the locking stuff that the thread safe one does. Yeah?
On one of the slides, you had an optimization regarding a timeout. Is that assuming that the timeout is set to the same value across all the nodes?
Does the timeout have to be set to the same values across all the nodes? Yeah, if you had a coordinator with a very tight timeout and the other nodes had a very long timeout, they might try to do the work. When they did the work, even though the coordinator had stopped waiting, it would send a message back. The message service detects that the read callback is gone and just dumps the message.
But then could the opposite lead to perception that an item isn't there when it is? So
Yeah. Any other questions? Yeah?
Do you know why there are so many singletons in the code base?
They've all been there from the beginning of time, and I guess it's just a choice of whether you write statics and singletons. So it's just the way it is. Another question at the back?
With relational databases, you get a query optimizer. What is the equivalent? Because you can have
Yeah, so that's in the, down in the DB service, there is an area that chooses which secondary index to run. It's based on, I hope I'm not getting this wrong, but I believe it's based on the row width histograms that are stored. So basically, if we think that if there's an index on the foo column and an index on the bar column, if the foo column index is bigger than the bar column index in terms of its average row sizes, I believe that's the choice to go with the bar column index because it's got less cardinality. Anyone else? No? Okay. Thanks, everyone.